f of that arrow. It preserves the domain and codomain. It takes the identity to the identity, any identity. This is, you remember, we normally don't even draw identity arrows. If I was a more official category theorist, I would have said this shows it preserves identity arrows because we don't draw them. Well, here I drew an identity arrow. And it takes composites to composites. When I draw this triangle, I'm telling you that this is the composite of those two. When I draw this arrow, I'm telling you that's f of this composite. Applying the functor to the composite gives the composite of the functors. Maybe it's worth drawing a more chaotic picture. If A is some category like this, well, we'll be getting more pictures. I'm not going to draw a more chaotic picture. I'll just start. Let's look at functors from the one object category to any category. This is, when I draw something like this, I want you to, this is some big network of arrows and objects. I'm not drawing lots of them, but the whole point of this dotted outline is this is some vague network. What's a functor to it from the singleton? Well, it assigns to every object here an object there, and it takes the identity here to the identity there. Again, here I haven't drawn the identity arrows because we don't draw them. And that's all. That's all a functor does. From the one object category, it just picks out an object. Takes that one object, just some object over here. So did I write that? Yes. Oh yeah, some more or less large network of objects and arrows. I don't draw the identity arrows. So the identity arrows just go along with the objects. So a functor from the category 1 to any other category just amounts to an object of that category. One is a pretty simple category. Its category is just all it's got, an object. A functor to it from it to another category just picks out an object. On the other hand, every category has a unique functor to 1 because all the objects have to go to that one. And all the arrows have to go, every arrow here has to go to some arrow here, but there is only the identity arrow there. So they all have to go to the identity arrow. Does that meet our defining condition? Well, sure. What we needed to know was that if you had a composable pair here, then it went to a composable pair. Well, but it goes to what it has to. It goes to the identity arrow, followed by the identity arrow, and the composite of those two is the identity arrow, and that went to the identity arrow. So yeah, just trivially, yeah, this preserves composition. The composition is automatically preserved because there's only the identity arrow here. And every equation is true if the only arrows you put into it are identity arrows. So the defining equation is true. So 1 is terminal in the category of categories and functors. And I hope when you look at this, you think, well, I mean, that's pretty persuasive. You want to say it's a terminal object in that category. It's a foundational problem because we don't really have a category of all categories and functors, depending on our foundation. But you can't help but think about it this way. You really have to think about the category of categories. And everybody always did. Eilenberg and McLean, when they put out their general paper in 1945, because it was meant to be the only paper ever written on the subject, they discussed foundations. They said there's a few ways you could approach this. But we'll come back to that really more on the fourth day than tomorrow. I'll give two solutions tomorrow. But now consider functors from the finite category 2 to any category. Well, 2 just looks like this. Now I've labeled the objects an arrow this time because I want to be able to indicate them over here. 2 looks like this. A functor looks like that. You pick out an object, you pick out an arrow, you pick out another object. The arrow has to go between those objects. The identity here went to the identity there. Again, this is why we don't draw identities, because you see you don't need them. A functor from 2 to any category just picks out an arrow in that category. I hope this looks simple to you, but you're also maybe thinking too simple. Why do I want functors to pick out arrows? But that's, the idea is simple. I labeled them, it's essentially, an arrow is essentially the same thing as a functor. In Laverre's theory of categories, arrows will be defined as functors. But functors from 3. What is a functor from 3? Well, it picks a value for each object. 1 went to there, 0 went there, 1 went there, 2 went there. It picks an arrow for each arrow that goes between the same objects. And the second condition set up preserves composite. Since gamma is the composite of beta and alpha, f of gamma has to be the composite of those. So it takes 3. Well, you pick any 2 arrows you like as pick any 2 arrows you like, so long as they share this object. They have to go to the same. They have to go to and from the same thing. Pick any 2 you like. Make those the definitions of f alpha and f beta, and then this one is determined. It has to be their composite. We call this a commutative triangle. Going this way around the triangle is the same as going that way. This is just the composite of those 2. We call it commutative. So a functor from 3 to A to any category is just a commutative triangle in that category. So looking at the functors from 3 is one way to reveal the composition law in that other category. It's a way to organize the composition. Of course, the composition law had to already exist before you could talk about functors. But this is a way to organize looking at them. So a functor from 3 to something is just a commutative triangle in it. Lots of constructions in math are functorial. The underlying set of a group. This is the category group of groups. It's got groups G and H and K in it, and they have all various arrows between them, lots of them. Now, the arrows here are group homomorphisms. So you say, well, they're really functions from the elements of K to the elements of G. Well, no, from a categorical perspective, I don't want to think of them as really functions. But they certainly relate to functions. There is the category of sets. And there's an underlying set functor. It takes H. What I'm going to write this way, the set of elements of H. Those are supposed to look like absolute value signs. It takes K to the set of elements of K. It takes G to the set of elements of G, which, by the way, they might have the same set of elements. Right? There's no reason they couldn't have the same set of elements. They're different groups, so they got different multiplication tables. But every group has. But what we do know is that a homomorphism it includes a function from the elements in. So this arrow F gets taken over here to an arrow that I'll write underlying set of F going there. Maybe these are the same set, and this is just a function from a set to itself. Or who cares? Maybe they're different sets, and this is a function from one set to another set. But the underlying set function, the identity on A, on G, does go to the identity on its. The identity morphism on G doesn't change the elements, so it becomes the identity function on a set of elements. And if you had FG and then their composite, well, I didn't draw that one very well. Well, yeah, let's suppose they're different. Yeah. The underlying set function on G well, that does compose to the underlying set function on their composite. So from a categorical point of view, I don't care what the elements of these groups are, but I do know there's an underlying set functor to the category of sets. If I think of this as a category of Zermelo-Frankel sets, these have specific elements. And then I'm sort of committed to saying these have elements in them. But if I don't think of this as Zermelo-Frankel, then I might not. But on any foundation, I do know the category of groups has an underlying set functor to sets. Groups have underlying sets, and group homomorphisms induce functions on those underlying sets. The identity homomorphism induces the identity function. Composite of two morphisms induces the composite of the induced functions. I didn't put this on the slide. There's another functor, the other direction. There's a free group functor. The free group on a set, you look at a set here and think of it as a set of letters of the alphabet, for example. What is the free group on it? Well, we need a binary operation, so we just write that as, given any two things in there, we just write one after the other, A, B, A, C. But it needs to be a binary operation, so now we have to be able to repeat this. We have to be able to multiply this by that. It's a string AC, AC, AB. I'll put this string in front of that one. I need inverses, so I also need A inverse and B inverse. The free group on this set, it's a group over here. If this set is A, call this A, let's call this functor F. F of A is a group whose elements are A, C inverse B, D, E inverse. There's strings of letters. There's just strings of elements here, where some of them might be inverted. And how do I multiply two strings? How do I multiply this string by B, F, G, E? Well, I write that after it. Except, how do I multiply it? How do I multiply it by EAD? Well, I write EAD after it, and I cancel those because that was the inverse and that was E. So my rule is I take strings of letters, or their inverses, they multiply by putting one string after the other and canceling inverses when you need to do that. So now I have a group. And it turns out free groups on sets are important as a technical construction. They're not super interesting by themselves, but they play an important role in various constructions. And that's also a functor, because if I had a function f from this to say a singleton set, the only thing in it was A, I know what this has to go to. This has to go to A inverse, because everything went to A. That has to go to A. That goes to A. That goes to A inverse. That also goes to A. That is A. That goes to A. Well, and then cancel out the inverses. I get A. Yeah. If I know a function on the letters, I get a function on the groups, on the free groups. So it's functorial. In a little while later, I'll come back to product functors. which are maybe more logical and in some way easier, I'm hoping that I can describe the fundamental group as a functor in a sufficiently clear way that you'll see the point of it. I don't want to give the impression that category theory is all technicalities. I want you to see it touches on actual math. Let's look at that two-handled torus. And I've drawn some loops on it. I didn't draw those. I found it online. But and it's got various loops. But it's also got more complicated loops. The fundamental group here, it turns out, every loop, no matter how complicated you can draw on the torus, can be collapsed down to some combination of these four, maybe followed backwards. So now we're looking at not quite a free group. Every path on this can be continuously deformed. I hope you get the idea that we take some path, we're going to continuously deform it. So, to take a simple example, let's start here and do a loop that comes down here and shows up on the back side and then reappears here and goes over here and goes on the back side. Do you see what I'm doing with this? And it comes back here. I can just narrow this down to look like that. That's the idea. I want to say the two are equivalent if I can deform one onto another. So I can that complicated meandering path, I can deform it down to this path B. Every path, no matter how complicated, can be deformed down to some combination of these paths. Some of them follow in one direction, sometimes follow the other. So this is the fundamental group, is the group you get. So an element of the fundamental group, it almost looks B inverse, A, C, D inverse. It almost looks like a string of these, except there's one equation that's hard to see. There's a certain combination of loops, a certain way of combining A, B, C, and D that you probably won't easily pick out by eye, that it turns out you can collapse down to a point. Well, I can show you which one it is, just so you'll believe me that you wouldn't see it easily. If you follow A, and then you follow B, yeah. So let's do a loop. We followed A, and then we followed B, and then we went backwards along A. So we went A, and then B, and then we went backwards along A, and now let's go backwards along B. And then you do C and D, and then you go backwards along C, and then you go backwards along D. That path collapses to a point. It turns out that path collapses to a point. I did not make this up. Riemann already did this. I learned it from Henri Poincaré. So the fundamental group, it starts out looking like the free group on those four letters, except that there's one complicated word that collapses to one. So anything that follows from that. I hope you'll see that on the one hand, this is an interesting way to study the topology of surfaces. If you were only concerned with the two-handled torus, you might not care, but this method is a good way to explore topology. It's also related to complex analysis, because there's a nice theorem in complex analysis that says that when you're integrating holomorphic forms, which is what you would do, integrating along this curve is the same as integrating along any curve you could collapse it to. Smooth deformations don't change the complex integral.
So I never have to integrate around a crazy curve like this once I know the integral around this curve here, or any nice version of this curve. So this would be cut a lot of ice in complex analysis. But now imagine mapping this torus continuously onto some other space. I'm going to take this torus and I'm going to map it onto, say, a sphere. How am I going to map it? Well, I'm just going to take this and I'm going to move it some continuous way and wrap it around the sphere. I just thought, well, I won't worry about that. What I want you to see is that's going to take any path here to a path over there. Right? If I had a continuous path here and I map the whole thing over there, it maps to a continuous path over here. And if I can collapse one path onto another, that collapsing will map onto a collapsing over here. Every loop in the torus gets mapped to a loop in the other space. And equivalent loops get mapped to equivalent loops. If I could deform one into the other in the torus, then take the continuous image of that deformation. I can deform the image of that map to the image of the other map over here in the codomain space. Equivalent loops get mapped to equivalent loops. And compositions get mapped to compositions. If I followed this curve and then followed another, take the image, follow the image of this curve, and follow the image of the other. Riemann knew all this 150 years ago. Every continuous function on spaces gives a group homomorphism between the fundamental groups. Loops on S get mapped to loops on S prime. Equivalent loops on S get mapped to equivalent loops on S prime. And composites of loops get mapped onto composite loops over here. Now they might collapse a lot. Maybe I took this whole torus and I mapped it to a single point here. Every loop here got mapped to a single point. So they all become equivalent over here. All these different paths I could follow, they all got mashed down over here. That could happen. In that case, I've got my fundamental group of this torus, and I've thrown the whole thing onto the identity element of some group. Well, actually, on the sphere, I didn't even have to do that. Right, the fundamental group of the sphere is just a one-point group. Every loop on the sphere collapses to a point. So the fundamental group here was just the singleton group. So when I do this map, all this nice complicated group all gets mapped down to a singleton group here. But in any case, whatever this map is, loops here get mapped to loops there. Equivalent ones go to equivalent ones. Compositions go to compositions. So this is a function. So this continuous map induces a group homomorphism that we call this. The fundamental group of that space is called pi of S. Fundamental group of that is called pi of S prime. The induced map, we just call it pi of F. We're naming it. I mean, I described what it is, but we're also giving it that name. Now, it's clear that the identity map leaves the loops alone. If I take this torus and just map it to itself by leaving every point where it was, then I left the loops exactly as they were. So I'm taking every element of the fundamental group and leaving it alone. I'm taking it back to itself. The identity map, the fundamental group functor applied to the identity map is just the identity on the fundamental groups, because they don't change anything. Mapping the loops from S to S prime and then on to further S double prime is the same as just having mapped them along a composite. It's the same thing. Because that's how I map loops. I just apply functions. So this preserves composition. So the fundamental group it's a functor. It's a functor from topological spaces to groups. It takes every topological space to a group. It takes every continuous map to a group homomorphism. It takes identity maps to identity homomorphisms. And it takes composite maps to composite homomorphisms. So it's a functor. On the one hand, it's exactly what it should be. Bernard Riemann pretty much knew this 150 years ago without any talk about categories. But he didn't say it very clearly. We now have a concise notation. This is functorial. Most constructions in mathematics are functorial, commonly. And I don't mean, well, most constructions in algebra and geometry, not so much in analysis, where people do very complicated things in analysis. Most constructions, the construction of the free group on an alphabet induces a functor from sets to groups. The construction of a fundamental group on spaces induces a functor from topological spaces to groups. It's just natural. It's what should be the case. I'm not sure what I can tell you that you need to know about this. And nobody really wants to ask. I want to stay with, let's go ahead and do the product functor now as a different functor. I'm concerned that I haven't conveyed this very well. But I mean, the picture is you've got any space. I've drawn this space. You've got this interesting group of paths. The paths can be very complicated, but we identify lots of them. We get rid of complications by saying the two are the same if they can be deformed into each other. When we get rid of all those complexities, we get a group, a nice thing. A group, it's got a binary operation, it's either got inverses. We simplify the whole complexity of the surface to just 4 paths and combinations of those 4 paths. And then we say, look, we can do that. Not only can we do this on all spaces, but maps between the spaces will preserve this group. That's why it's important. It would be just a curiosity if the maps didn't preserve it. It's important because the maps do preserve it. And they preserve composition. And it's very easy to see that if I didn't change anything here, then I didn't change anything in the group. And it's not hard to see the way this works. If I'm given this map, and then a further map to some other space, well, what I did with the loop was I just followed this map and then that one. And so, of course, what I did with the space was the same as the composite. What I did with the loop was the same as the composite. So this thing preserves composites. And I guess I should have written this on the slide. So now let's forget this particular space. S got mapped over to S1. The loops here got mapped to loops there. So the fundamental group on S, by F, got mapped by an arrow that I simply named this. Again, the magic isn't in the name. The magic is in describing what I actually do. S1. No, prime. On the slide it's prime, not 1, it's a prime. Yes. If I map this to some further S double prime, then I get a group map here to S double prime. But what I did with this loop was I just mapped it along the composite. So I might as well have mapped the loops along the composite in the first place. I will get the same result. This is pi g. I would get the same result as if I just mapped it along the composite in the first place. And this helps it. So now we can do constructions. If I want to do a construction in this space, maybe I can more easily do it in another that maps onto it, and I know it'll be conveyed along that map. It might still be hard to draw conclusions from, but I can do that. So now let's look at another example. The point here, I don't expect you to follow the topology very closely unless you've already learned the material, but I want you to see if this is actual math. Now I'm going to give an example that comes straight out of category theory. I will describe it thoroughly, unlike this example, where I wave my hands a lot. On the other hand, I don't want you thinking that the examples all come straight out of category theory. Right? They're easier to give when I'm discussing category theory, but it's not the only thing that happens. Suppose every two objects, A, B, in category C. Now I just realized a disadvantage I have. On these slides, I indicate categories by using boldface. Yeah, I indicate category. I can't do that in handwriting. I can't handwrite boldface. So I'm going to handwrite calligraphic. Have a selected product. The selected product, I'm going to write it this way, but remember, for us, a product always comes with projection arrows. It's meaningless to just say that the object is the product. It's the object together with the arrows is the product. Suppose every two objects in this category have a selected product. I've picked one for each pair of objects. Now, that doesn't have to mean axiom of choice, because maybe it's a special category where I don't need choice to do that. For example, the category of Zermelo-Frankel sets. I do not need choice to pick a standard product for every two Zermelo-Frankel sets. I just take any standard definition of ordered pair. Each definition of ordered pair does that for me. In general, a category where every two objects have some product, if you don't assume something like choice, there may not be a way to select them. But here I'm making that data. I'm saying, suppose my category does have selected pairs for each. Again, this is not exactly the full strength of choice, because it's a unique, I'm picking a unique one. I'm saying there's a function, but it amounts to assuming choice in general. Now suppose they do. Then for any object B, we will define a functor. Blank cross B that goes from C to itself. And I think in the notes later on, I'm going to call this category A, but I can't write a calligraphic A very well. So, what do I need to do for this, to define a functor? Well, I need to know for every A, I need to know what is A cross B. Well, I said I've selected it. And for every F from A to A prime, I need F cross B. From A cross B to A prime cross B. A functor gives a value for each object, but I sort of told you what value I want in the object. But now I need to know that for every arrow, I get an arrow between those. how do I know that there is such a thing? Define it by, well, look at my data. How am I going to draw this? Yes. I've got my product of A with B. And I've got an arrow from A to A prime, F. Now I've got a product of A prime with B also. I want an arrow from here to B. How do I always define an arrow to a product? You always define an arrow to a product by defining arrows to each side. Because that's the definition of product, is that if I've got arrows to each side, I've got an arrow here. Now I've got an obvious arrow to this side, namely, well, this is P1, namely FP1. What arrow am I going to use over here? This is kind of categorical thinking. There's an obvious arrow from B to B. And this goes back to that constructivity thing. How do I pick an arrow from B to B? I don't want to pick one randomly. I really only know that in general there is one. In general, an object may only have one arrow to itself. Every object has an identity arrow to itself, but it may not have any others. So the only thing that makes any sense to pick here is the identity arrow. That's the only arrow I know always exists. If I want to do this in full generality, which I do, that's the only arrow I could put there. So this composite is also P2, the same P2. Now, by definition of product, there's a unique arrow here that I can name it FP1, comma P2, but that's just a name. But the defining property of it is, I'll call these Q1 and Q2. I'm not going to call them P prime 1 and P prime 2. That's too hard to read. The defining property is Q1 of this thing, of this arrow, FP1, P2, is FP1. Right, that's always my defining problem. Composing with Q gives you that side, Q1, and composing with Q2 gives you that side. That's always my property. Composing with Q2 gives you that side equals P2. Now the notation is nice. These are projection arrows, projection of a pair. The first projection on the pair takes you to the first element. The second projection takes you to the second. But remember, these aren't ordered pairs in any set-theoretic sense. It's just an arrow that has this property. So on the one hand, I say I'm going to define this arrow by this diagram that amounts to saying I define this arrow as making these two equations true. How do I know there's an arrow making those two equations true? Well, I suppose that we have products. It's the definition of product. Again, going back to that constructivity thing, this supposition is not very constructively plausible, but it's a supposition I made. So now, for every function in A, I've got this function also in A. This is a functor from A to itself. But given this function, I've got that function. It's the thing that makes this commute. Now, what does it take to be functorial? Well, for functoriality, I need to know first the case where this is the identity on A.
if this is the identity on A, then I need to know that, well, then this is A cross B. This is now P1 and P2 because it's A. It's the same A both places. How do I know that this arrow is the identity? Well, I know that this arrow has this property. Okay, this, now F was the identity, so that's just the pair P1, P2. Well, so what I want to know that P1 paired with P2 is the identity on A cross B. That's what I want. What I have I know that whatever this is, if I compose it with P1, I get this composite, which is P1. I know that P1 composed with the pair P1, P2 is P1. That's making this look like an identity arrow. And I know that P2 composed with this pair is P2. That makes this look like an identity arrow. And an arrow is uniquely determined by which of these equations it satisfies. So, P1, P2 is the identity on A cross B. It satisfies an equation that only one arrow satisfies, and that the identity satisfies. It's the identity. So what that tells me is one sub A crossed with B, that's defined as the arrow here that makes this commute. And the arrow here that makes this commute is the identity on A cross B. Yes, I do know that. This functor preserves identities. Now I also need to know, let's go back to the general case here. FP1. Oh, and this is in general. Now suppose I have the composite of this with G. Well, on the one hand, G cross, so this is by definition. This is by definition F cross B. By definition, G cross B goes from A double prime cross B. It goes from A prime cross B to A double prime cross B, and by definition it makes this square, this makes that square commute. But what's the definition of GF cross B, the whole thing cross B, is it makes this outside square commute. To define G cross B, I look at this diagram, the arrow that works with those is G cross B. To define GF cross B, I look at the outside square. The arrow that makes the outside square commute is the composite crossed with B. any two arrows, if these squares commute and those squares commute, then it follows that the outside did. I need to know, F is defined by saying this composite equals that one. But then, and this is defined by saying that this composite equals that one. So then composing with this is the same as composing with those, but composing with those is the same as composing along there. And here, composing here is the same as composing there, which is the same as composing out there. So right now I'm waving my hands pretty fast, but I'm trying to keep it intuitive and introductory. So indeed, if these two squares make if these two arrows make the equations for those squares hold, then their composite makes the equation for the whole thing hold. So yes, F cross B, no, I'm writing in the wrong order. G cross B, composed with F cross B, makes the same square commute as GF cross B. And they're defined by making the squares commute. Now let me put that more, I'm afraid I didn't put that so clearly. For F here, to A prime, we got F cross B there, to A prime cross B. And this is the identity on B. Now for G here, we got G cross B here. Also identity on B. We know that this composite is the same as that. Going this way is the same as going that way. And going this way is the same as going that way. That's our definition of F cross B. We know that going this way is the same as going that way. And going this way is the same as going, that's our definition of G cross B. What we want to know, we'd like to know that going down this whole thing and then over is the same as going across and over. And going down this whole thing and over there is the same as going across there and over. But going down here and over there, we know is the same as going down here and that way. And we know this is the same as going over there and then that way. So we do know that this composite followed by that is the same as that composite. We know that, we want to know that going down here and over there is the same as going across and over, but we know it's the same as going that way, and we know this is the same as going that way. So indeed, what we want to know this. What we do know is, let me call this R1 and R2. We know that R1 followed by this composite equals R1 followed by that. And we know that R2 of that composite equals R2 followed by the other. And we know that a map is uniquely determined by its compositions with R1 and R2. So we know they're equal. So this is a functor. So we know that product with B is a functor from the category C to the category C. It takes any A to A cross B. It takes any F to F cross B, which is defined by those diagrams. And we now know that it does take identities to identities. It takes composites to composites. So it's functorial.
as it should be, as it had better be. This is technicality, but we would not like the subject if this technicality didn't work. But it does. So now, I wish that my mathematical example was more radiantly clear, and I wish my technical example was less technical. But at least I've given you one of each. You see, it works with fundamental groups, it works with constructions inside category theory. So Riemann used this kind of idea a long time ago without organizing it. Category theory organizes it, and this again, what I want to say over and over, category theory is not a weird machine that comes in and changes things, it's a device that organizes things. If you feel it left Riemann's insight sort of unchanged, great. I can tell you that it generalized Riemann's insight very much. It did change it that way. Grothendieck does a lot of stuff that Riemann never thought of. But it's close to what Riemann was doing. Functors are a natural idea. But functors make no sense without natural transformations. So next we do natural transformations, and as I promised, I will try to convey to you what's natural about them. Yeah.